talk about section 1.1, functions and models. We're going to look at the different types of determining whether a table, a graph, or even an equation defines the functions. We're also going to learn about their domain and range of those functions. We're going to look at creating a scatter plot of a set of ordered pairs and use function notation to evaluate functions. And we'll also wrap in a little bit of real-world information using mathematical modeling. So let's start with our definition of a function. Now, a function is a rule or correspondence that assigns to each element of one set exactly one element in the second set. Now, there's definitely some new terminology here. Most people hear about it as a function has a domain and range, and that's not exactly the true definition of a function. Now, domain and range are probably not new for some of you guys. So a function is basically a rule that corresponds that having an element in the domain, which we call the first set, goes to exactly one element in the second set, which we call the range. Now, a function itself may be defined by a set of ordered pairs. It can be a table, it can be a graph, it can be an equation, or it could even be a verbal description. Okay, so when we talk about this, you'll notice I didn't actually refer to X or Y at all. Functions are not limited to just algebra. So there's a lot of different places in which functions come into play, but we still try to use the words domain and range. Now, even though we do try to use those words domain and range, we also want to remind ourselves that think of it as basically that domain is that input value. Okay, it's the first thing that we start with, and the range is going to be that output value. Okay, and again, like I said, it can be as a set of ordered pairs, it can be a table, it can be a graph, it can be an equation, or even just a verbal description. So the first thing when you come to a college, you're assigned a student ID number. So if I have a student ID number and it gets mapped to a student's name, we know that each student ID number only goes to one student, right? So therefore, that is actually a function in itself. So let's take a look at this in a little bit different, kind of more word problem, more what we're used to seeing in math class. So suppose a child's normal temperature is 98.6 degrees Fahrenheit, and the only thermometer available is Celsius. Now, you take a kid's temperature and it indicates that the child's temperature is 37 degrees. Now, what we want to know is, does this reading indicate that the child's temperature is normal? Well, again, we're used to Fahrenheit in the United States, but in other countries they use Celsius. So because that has happened around for quite some time, there has actually been a formula developed to go from Fahrenheit to Celsius. Okay, so the formula itself is F equals 9/5 times C plus 32. Okay, now we were told that this is normal, but this is what we figured out the kid's temperature was, and we want to know, is this the normal temperature? So what we're going to do is we're actually going to plug 37, we're going to input it in for the Celsius and see what we get back out. Now, if we get the same item back out as 98.6 degrees, then we know it's normal because that's what we know is given as a normal temperature. So as you can see, I've already plugged in 37, so it's 9/5 times 37 plus 32. So again, multiplication comes first, then we add that 32, and everybody should have gotten 98.6. So therefore, this does match the original up here, and we can see that it is actually normal. So the kid's temperature is fine. Now, remind yourself that it could be in that kind of simple context of a word problem style, but we can also talk about functions in a little bit different formats. We can see them as beautiful pictures or graphs, or we can even see them as tables. Now you'll see here that each one of these is actually the same, okay? And what we've done is we've created our first scatter plot. A scatter plot is just basically all the ordered pairs in a visual representation. So as you'll see here, X is -5, Y is -7. Here's X equals -5, right? And if I go down here, I'm going to see my Y value of -7. So this is that beautiful ordered pair, -5, -7. And I can go through and you'll see that all of these match up to these ones on the side here in our table. But for each of these, we want to determine what is the domain and what is the range. Now, you'll notice here, all of these dots are not connected. Okay, same thing over here. When I start looking at this, none of these are actually like the same, and there's not this kind of steady flow between the table. And it may not be as obvious on the table, but if we come over here to the graph, we can see that they're all kind of spread out. So if you see it visually up here, what I would do is I'd go through each one of these points and I would kind of remind myself what they are. So start always at the origin and move over. So we have to move left. So we're going negatively 1, and then we go up 6. So this point right here is left 1, so -1, comma 6. And again, same thing here, kind of take a peek at it. So I go 1, 2, 3 to the left, and then it's 1, 2 down, so -2. Okay, again, that's going to be that point. Again, as you notice, they kind of all match the ones that are over here. So what is my domain? Now remember, domain is your input. So what did I do first? I always moved left or right first. So that's going to be my input. So in our case here, our domain is the input. The first movement we do, we move left or right first. So the domain is going to be all of these x values, and the range is going to be that second thing. So the first part was we moved left 3 and then down 2. That second thing that we did to match these two numbers together, that's going to be our range, which is our y values. Now, this is why a lot of us think that domain and range is only x's and y's, but it's not, as you guys saw previously. Okay, now, how would we name that out? So normally when you see it in either one of those formats, I would strongly suggest write down what all those ordered pairs are. And again, remember, anytime that you have an ordered pair, so let's kind of just make a little note here. Anytime I'm talking about an ordered pair, they're always written as x comma y. So the x is first, the y is second. Again, my first is the input, the second is the output. Now, as I write the domain should only be the x's. So I kind of want to just take a look at those x values and write them, okay? And I would just go ahead and write them all side by side with a comma separating them. Now, because these are they're not all the same and they kind of have space like separation between them, because it's not a continuous numbers, I'm just going to use these braces on either side here and just list out those numbers. Now for the range, again, that's going to be that y value, that output. And what you're going to do there is you're going to want to take all of those. Now you'll notice as I'm looking through these, I've noticed that -2 and -7 both repeat. So even though as you take a look at those, okay, and I'm going to highlight them to bring it to your attention a little bit there, we see that this y value is the same as this y value, and this y value is the same as this y value. Oh, I forgot a comma. So even though they're technically the same, that doesn't necessarily mean I have to worry about them being in the range twice. So all I have to do is I actually really just need to write them out. And if anything repeats, I only need to write it one time because I've already written it once. Now, remember, again, we said it could be scatter plots, it could be these nice pretty tables, but it could also be a graph that looks like this. Now with this graph here, we need to determine the domain and range, but it's not all these individual dots. It's actually got some space between it. So remind yourself that for domain is that input, which in our case here, when we're looking at a graph like this, our input is going to be the x's. And on our graph here, as I take a look at the x's, this is that left to right. So we always want to go from left to right. So I'm going to start at the origin and I'm going to go as far left as I can until I get to the point I need. So as far left, and as we can see there, it happens to be -3. Okay, and then if I keep moving on the graph as far right as I can go, and notice it's kind of got a stopping point here, where does it actually stop on the x's? Well, that point is +3. Okay, So there's two different ways in which I can write this. I can write this in what we call a interval notation. Now with interval notation, which is our preferred method, interval notation is going to go from where did I start and where did I end, because this is continuous, like they have constant flow. Now you'll notice I'm going to put these brackets on left and right side. Now the reason why I'm using the bracket is because this is a closed circle, meaning it comes to a full stop. So you're going to use a bracket on the number. And the same rule applies over here. Now, if it was an open circle, I'd use a parentheses. Now, another way in which you can write this is also, you could easily write this as more of a algebraic expression. And you can say that all of your x values happen to be between -3 and 3. Now, we do know that we actually get to -3, so I'm going to have to put an equal sign underneath there. And same thing with 3 itself. Again, if it was an open circle, I would just say that it gets close to 3, but not equal to it at the bottom. Now my range, remind ourselves, these are those outputs. And again, we kind of think of these more as the y's. This is why everybody associates domain and range with x's and y's. Now, y values, as I look at my graph here, happens to go from the vertical area. So this is where we go from low to high. Now, you'll notice I'm saying low to high. Please do not start off with what the high number is. It's got to go from low to high, especially when you're talking about the interval notation. If it's not written the smallest number to the largest number, it will count you wrong. Okay, and we can kind of see there that we've got what looks to be about -30-ish. And then as I continue going up to my highest point on the graph, which is over here, which seems to be about 40. Okay. And again, if I actually hit those points, I'm going to put a parentheses on it. And again, if really the only way you can say that it doesn't hit that point is if there's really an open circle or a asymptote. And if I'm going to use the other algebraic notation for it, remind yourself that with that, again, you're going to use that y is in between with the less than symbol there with a line underneath to represent that it equals it as well. Okay, so either way we'll work on that. Okay, so it's typed out a little bit better there. Now again, remember I kind of eyeballed it, so I said it looked like it was about -30. Now when you are doing your homework, you're going to have grid lines, so it's going to be a little bit easier for you to see, so you don't actually have to eyeball it. And you'll actually see that this one actually stops at -27 and it actually goes to 39. So when you are looking at your homework and when you do that, you'll have a little bit better grid lines to kind of go off of. So let's try this one here. Now this one's a little bit different because you'll notice there's this beautiful arrow on the side here. So again, we always read left to right when we talk about that domain. So again, left, I need to add extra T there, left to right, okay? And that's going to be that domain, always left to right. Now, how far left does this graph actually go? It looks like it keeps going and going and going left, right? It doesn't actually look like it ever stops going left. And if it doesn't ever stop going left, what's going to be super far out on the left-hand side is basically what we call a negative infinity. Now, what's super far out on the right-hand side is also a positive infinity, but you'll notice my graph literally keeps going left, but it doesn't actually keep going right. It actually kind of stops right here at this beautiful point, okay? So that right there lets me see that my domain is going to be basically from that negative infinity all the way to that 4 point. Okay. Now, one of the things that we have to remind ourselves about infinities is that infinities, I don't know exactly what that number is, so I can't say it ever equals it. So I'm going to always use a parentheses on it. But 4 itself, I know the number. I see that it actually hits at 4, so I'm going to put a bracket on it. Now, if I am looking for the range, remember low to high is going to be my range. Now, with that, Start low, the lowest point on the graph. And again, remind yourself, everything that you see here that's in black, that is just kind of a guider line. What I'm really referring to is for the graph of the function is I'm referring to this blue part. So taking a peek at that blue part, and I look for where's the lowest point on the blue part. It's right here. But again, I don't need 4. 4 is an x value. I need to know what is that low versus that y area. And I can see there that it's kind of going from 0, okay? So it looks like it's 0, and then it kind of moves up from there. So we're going to start at 0, and again, bracket on it, because I can see that it actually hits that y value of 0. It's just got an x attached to 4 to it. And then I'm going to follow it up, up, up. Now, understand that even though it hits 2, it keeps going up. We're not talking about here to here, just looking in this direction. We're literally talking in the sense of outside of it, like how far up does this graph go? Now, again, we got here and we said it goes left forever, but it also has a bit of a upward motion. So it's slow, but it does move up. It's just a really slow upward motion. And again, if it goes up forever, just like we talked about the positive and negative infinity here, if it goes up forever, it's going to go up to infinity. It just might take a very long time to get there. Okay, so make sure that you're really careful in watching that arrow as you see there. Now with infinities, we don't normally use the same type of interval notation versus algebraic notation with the inequality symbols. We prefer the interval notation with the infinities. However, again, it could be a little different if you would like. So I'm going to go with that domain being from negative infinity to 4 with that bracket on it. But if I switch that up to my algebraic notation using an inequality symbol, like a less than or equal to, this would look like x is less than or equal to 4. Now, again, think about it. X value is 4. That's the highest x value I have. But I have everything that's less than the 4 there. So here I have 2, here I have 0, here I have -2, here I have -4, here I have -6, here I have -8, and it keeps moving to that left. So this is why this interval notation, it looks a little bit better, and we like to kind of lean that way, but we should know what the inequality version is as well. Now, again, we talked about the range starting at 0 was that low point, and then it just keeps going up. Again, really do prefer the interval notation, but when we talk about it in terms with the algebraic, that's going to be that y is greater than or equal to 0. Because again, it starts at 0 but moves up, so it's greater than it. Now, not everything we have is going to have a picture related to it. Some of our stuff is very much in a word problem setting, and we do actually have to take a peek at it in sense of the word problems. So with that being said, for the following, we're going to determine whether or not the indicator relationship actually represents a function. Now, remember that domain is my input, range is my output. So I definitely want to be very, very careful with all of this, okay? Now, the PC industry celebrated its 35th anniversary in 2010. Now, the US sales of a personal computer in millions of dollars by year X is shown in the table on the next slide. Is X a function? Now, let's talk about this before we see what that table says. S is personal computers. Now that's in millions, represented by the year X. Okay, so millions of dollars, that's sales of them. So the selling, but you have to know what year it is before you can figure out what sale it is. So we can already kind of see what is our input versus our output. So here is a really beautiful table. And again, you'll notice the year, and they kind of gave us the help that this is X and our sales is going to be S. Now, again, remind yourself, do not get attached to X and Y. X does not always represent the domain. It depends on how it's labeled. In our case here, X is that first input column and S is the output column. So yeah, but S is not Y in the sense of they told me that it was Y. We called it a different letter. Okay, so is S a function? Well, let's take a peek at it. Do any of my years repeat? Well, no, it looks like they don't. Now, do each one of those years goes to a unique number. Make sure that it doesn't say like 2010 goes to 70 and 2010 goes to 80. Then I could say, no, it's not a function. So in our case here, this looks like it actually is a function. Now, since it looks like it is a function, again, our input is our years. So this is the input. This is kind of where we start. And this is our output, which would be our sales. Okay. Now, the domain, since is the input, that's going to be all those years. And our range is going to be the sales itself. Now, before we jump into something else, I want to go into the calculator side of doing a scatter plot. Now, we looked at a scatter plot a moment earlier about how it was kind of written out, but we do have this thing called a calculator that does help us with scatter plotting and showing it in the calculator. So if you've got a graphing calculator, go ahead and pull it out and kind of follow along here. So the first thing I'm going to do is I'm going to hit the Stat button, and I'm going to hit Edit. Now, I'm going to make sure that my calculator says list 1, list 2, list 3, list 4, and so on. If it does not say list 1, list 2, list 3, list 4, and so on, so say one of your lists is missing, what you're going to need to do is actually reset your calculator. So second, plus sign, reset, okay, and then all defaults. Okay, that will nicely do it there. And so then when you go back to Stat and Edit, it should show up. Okay. Now, if you do have list 1, but there's, say, some numbers already there. Okay. So say there's already some numbers there. What I suggest you do is go up and hit the list 1. So see how I've moved it up and highlighted it, and then say, I want to clear that list, enter. Whatever you do, do not hit the DEL, because think about it. DEL stands for delete. I don't want to delete the list. I want to clear it. Okay. And then I can type in basically my X values into the calculator. Now, it's going to work just like Excel in this sense that what you're going to do is you're going to start by typing them in. And when you hit enter, it's going to execute it and move to the next one down. Okay. Once you have those all in there, just go ahead and move over to the list 2, and you can start entering in those numbers. Now, again, the same rules that we did for clearing the list in the first place will also still work here. So if you need to clear list 2 before you start typing in things, that is perfectly fine. Now, one of the things I want you to do, and again, you'll notice I made a mistake, but I did it on purpose here, is always go back up and just double check to make sure that everything you have is correct. You are typing in a lot of stuff into your calculator, and that could make it really easy for you to make a mistake, okay? And it does happen. And again, just be very cautious of it. Now, I do want to bring to your attention that when you saw 46, I typed in 46.0, but really does a 0.0 have to be there? No. Now you'll notice down here at the bottom, I said 1,220 and it should have just been 122.0. If you make a mistake, all you need to do is highlight it and then start retyping that cell and hit enter, and it will update. Now, this is putting it into the list. Now, to make that scatter plot so we can visually see it, what I'm going to do is I'm going to hit second y equals. Now, I say second because notice right above the y equals button, it says stat plot. So second y equals, and we're going to hit enter to go into plot 1, and we're going to turn it on. So make sure on is blinking and then hit enter so it moves that black box over the on button. It should kind of default to a lot of these, so kind of make sure like what you have there. So this is our scatter plot, and we want it to take the stuff from list 1 and list 2, like what we did. Take your pick of how you want the dots to show up. I do recommend the box just because it's a little bit easier to see. And then pick your color. Okay, you actually have a couple of colors. Now, if you do not have a TI-84 Plus color edition, you're not going to see these colors. So that is something that could happen. And if that's the case, that's perfectly fine. It can always be done in black and white. Now, once you have all that done, what you're going to do is you're going to hit y equals, clear out anything that you have in here. Make sure this is fully clear before you do the next step. Okay, so second y equals turns it on. If it's already on, you're nice, but if not, you just hit enter, go in, say on by hitting enter, and then you're just going to hit back to the y equals button and make sure that there's nothing in y equals. And you'll notice I really quickly cleared it, and all I had to do was just hit the clear button and it does that. Okay, then you're going to hit the zoom button and then you're going to do number 9. And what that does is that actually is going to graph all of these plots so you don't have to play around with the window. Now, we will talk about how to make adjustments to the window because there are some problems later in the later sections that we will need to adjust. But you can visually see how it looks, which is kind of cool and nice, that it does look really interesting compared to the numbers. So sometimes you might see it in a table, sometimes you might need to visualize it, but we can see there that it works really nicely. Okay, so what if it doesn't give you a table? How do I look at an equation and define y as a function? Now, again, the reason this works the way it works is basically, remember, for every input, there's only one output, okay? So for every input, there's only one output. And if you can have multiple outputs, that's not really going to be good. So let's take a look at this first one that we have. Now, this one is a little unique, and let's think about it. If you think about it really closely, the relationship is not a function. And how can it not be a function? Well, there can be more than one output for every input. So think about it in the sense of, let's see, what if I choose something that would make it work? What if I choose 3? Okay, so 3 in particular, we square it, that's going to give me 9. So 9 equals 4x minus 4. So I'm going to have to add the 4 over to our 9, then divide by 4. That's going to give me one answer and one answer. But when you actually think about it, what if that was there? It could have easily gone the other direction and had a number very similar to it. Okay, now these are really hard to graph in the calculator, so let me give you a small hint, and this is actually a really fun hint here. So if this says y squared, notice the button in your calculator at the very top left corner says y equals. If you can't type in is y equals, and this says y squared, we don't have y squared, we have y equals, then it's not a function, okay? So that's kind of what makes this really kind of interesting and cool and unique, is the calculator can kind of give you a little bit of a hint whether something is a function or not, okay? Now, let me show you what the graph actually looks like. Like I said, it is a little on the unique side just because it's not necessarily what you're thinking of when you look at it, okay? And that's where some people struggle with the visualizing of these ones because they look very unique and different. So in order for you to see it, again, remember the calculator does not graph this. I am having to do kind of some shifty stuff to make it graph it. I'm actually having to graph 2 different things to make it actually show up as one big thing, but it does work. So let me get there so you can see it. And this is what the graph actually looks like if you were to see it visually, okay? And so even though we said x equals 3 gave us one number, it can actually give me the negative version of it as well. And that's not very clear by looking at it, but the best way to describe it is if there's y to any power, it's not going to be a function itself, okay? Now, if I take a look at the second function here, y equals negative x squared plus 6x. Now remember, I said the rule of the road here was if you can take the calculator and say y equals, okay, and could you type this in? Well, yes, it says y equals, and that's what it says here. So therefore, that is actually going to be a function. So for each value of x, there's only going to be one y value that comes back out. Okay? Now, you notice I kind of kept referring back to the graph there. And there's some things that you can't put in the graphing calculator, but you might be able to be given a visual picture of it, and we want to determine if it is a function or not. And to do a visual version of the test that we just did, it's called the vertical line test. Now, a set of points in a coordinated plane is the graph of a function if and only if no vertical line, again, there's that beautiful keyword there, so I'm going to point that out. No vertical line intersects the graph more than 1 point. Now, more than 1 point means it has to hit twice or more. So what I'm doing is I am looking at this blue line here, okay? And I'm checking to see, does any vertical line, if I take any vertical line, ever hit more than one time? And just kind of in general here, here's this one here. Look, it only hits once, but if I keep moving it, it's still only going to hit one time. So this one's going to be a function. Now over here though, again, this is one that we just looked at kind of in a bit more of a visual representation. I can take that vertical line and you'll notice it hits here and here. Again, we don't care about this black background stuff. These are only guiders to let us know what the function should be situated in a 3D location or 2D location. But the blue is the function I'm actually looking at, whether or not it is a function. That's kind of what I'm looking at to see if it is or isn't. And the vertical line, this red line is kind of in your imagination, and you'll notice it hits once, twice. But even if I move it over here, it hits 1, 2. Even if I hit it here, it hits 1, 2. But if I move it over here, it's only going to hit one time. But if at any vertical line, that's the kind of no vertical line, meaning any one that I see has to basically make this work. And that's why this one's not a function. Okay, so now that we've seen what we call visually as a function or not, sometimes functions are also written as equations. Now, one of the things that a lot of people forget about functions is we use this beautiful function notation. So we're going to say f of x. Okay, so that's my function notation that I have there. Now, with my f of x, please remind yourself that 2x to the third plus 5x squared minus 28x minus 15, that this part here is the function that we're actually putting in the graphing calculator to graph it, but f of x is the same thing as if I had just said y equals, okay? F of x and y are exactly the same thing. It's just a way to do function notation, okay? So instead of saying y equals, we say our function is evaluated at some number. So we're going to use the point shown on the graph to actually find f of 2 and f of 4. Now, when I say f of negative 2 here, f of negative 2 means x equals negative 2 when y equals, and you have to go find it. So that's basically what this function is saying. It's the function evaluated at negative 2. The function evaluated, oops, we'll just say that, evaluated at, sorry, my T became an X, at x equals negative 2. So when x equals negative 2, what is y? So we're going to take a peek at this graph and look for x equals negative 2. Here's x equals negative 2 right here, okay? And we're going to follow it up to the blue line there, and we can see kind of where it lands. Again, right now we're kind of eyeballing things, so it looks like it maybe might be about 41, 42-ish, okay? And so this point right here on the graph, this part right here, that is going to be that really nice f of negative 2. So now we need to know the y value of that to be able to kind of work our way through that. And like I said, that's kind of where we were eyeballing. It looks to be about maybe 42, 43, maybe like it's not too close to 41, but maybe 42, 43. Okay, now if I do f of 4, same rules are going to apply, but think about it. What's our x value going to be? 4. So I'm going to find my x equals 4. So here was x equals -2. Okay, that's why we did there. So I'm going to go from 0, 0, and go 1, 2, 3, 4 to that right-hand side. And here's x equals -4 or +4. And go 1, 2, 3, and a bit. It looks like to be about here. It looks like where it actually hits 4. So it looks like that's like maybe 78, 79. It's kind of close to 80. It's not at 80, but it looks like it may be somewhere in this area. Okay. And this is where you kind of eyeball it. So it does get a little hard to see what it actually is. Okay. So you're going to be kind of making an observation that basically -2 is around maybe 45 and +4, our x value is around maybe 81, 82, 83, 83 looks like it's a little off. So I would definitely say like either 81, 80, or 79. That's kind of where my guess would. Now, again, we are observing, which means we're eyeballing. Now in math, we don't really like to eyeball stuff. So what we do like to do is we like to actually figure out what it exactly is. So let's use the equation instead to find f of -2 and f of 4. So instead of looking at the graph, let's actually do the math part of it. So when I say f of -2, what that means is everywhere I see an x value, okay, and I'm going to highlight all those x's for you to kind of bring it to your attention. Here's an x, here's an x, and here's an x. You'll notice I didn't highlight this one because that's the x they gave me. So I'm going to take that -2 and plug it in for each one of those x's. Now, you want to be very, very cautious when you're plugging in because this one has a power, this one has a power. Now, this one doesn't, but it's got a number in the front. So anytime that you're plugging in, especially if you're plugging in negative numbers, please make sure to plug them in with a set of parentheses around them. Otherwise, you might end up getting the problem wrong if you do the math that way. Okay, and we can see that -2 third power is -8, -2 squared is 4, -2 is just staying itself, and then we're going to multiply all those by their coefficients in the front, and we end up with 45, which was about where we kind of eyeballed it. But again, we were just observing, this is going to be exact. So let's try this again, but this time, let's do this with our 4. Now, even though my number here has changed, the placement of where I'm putting that 4 is still going to be in the same area. We don't change wherever we plug it in. It's always still the same. So we're going to get that 4 to the third times 2 plus 5 times 4 squared minus 28 times 4 minus 15. So again, I'm going to do those exponents first because order of operations says that's what I should do. And then again, work your way all the way to simplifying it down to get 81. And again, we can see the exact answer is 81 there. Okay. Now, as we look through all of these, guys, do remember that not everything is going to be written out in such simple terms as do this. Okay. And what I mean by simple terms, and again, this is where I guess some people get confused. Use the equation to find this. Well, that's not very realistic. That's not normally what a lot of your jobs are going to say, like, do this and just that. Normally, they're going to propose, especially if you're in like a workplace job or a business style job, they're kind of going to propose it to you and be like, so here's what we have. Can you please explain to me what the function means for the year 2020? Okay. So the point of the graph is given by the following number of elderly men in the workforce in millions as a function g of the year t for selected years from 1950 to 2050. Okay, now find and interpret g of 2020. So again, look at what's there. That says my input is 2020. Now it does say t here, so again, we're not using x's, but that's okay. So we're going to find 2020, here it is, and we're going to go up until we find our point on the graph. And again, this is where I said sometimes it's going to work out really nicely. Sometimes it kind of looks a little weird, but we can see exactly here at 2020, it happened to be 21. So my input was 2020, my output, again, as we can see there, and they kind of gave us the hint above it, is 21. So what does that actually mean? If I put in the year 2020 and the output's 21, what does this side over here represent again? Well, the points on the graph are given the number of elderly men in the workforce in millions as a function of the year time. Okay, now we call the function G, this is the name of the function, but T, our year. So in the year 2020, we have 21 million elderly men in the workforce. Okay. And again, that's kind of where we look at it. Now, when they say the word interpret, those are going to be those types of problems that you're going to have to write a little bit, or you're going to have to choose an answer that's a little bit more wordy. It's not just disordered pair. Okay, that's not necessarily it. And it's not just going to say G of 2020 equals 21. This is kind of a word problem I did ask you to interpret, so we'd have to kind of think our way through and have a little bit more wordy style answer. Now, let's take that same problem. And let's say, what is the input T if the output is 19.6 million? Okay, so if the output is 19.6, so here's my output side. And if that's 19.6, well, there's 19, there's 19.5, 19.6, what was the input? So what year gave that? That would be 2030, okay? So we can see there that in the year 2030, it had that output of 19.6 for us. Okay, again, still kind of looking at this graph because it's really awesome to take a peek at these graphs. So what can be said about the number of men between 2020 and 2040? So again, look down here at the timeline and 2020 to 2040. So 2020 started at 21. Then we went to 19.6 and then 17.3. It looks like it's kind of moving on a little bit of a downhill slope, right? So when we talk about that downhill slope, we don't normally say the word downhill. We're going to say the word decrease. It looks like it was decreasing. So the number of elderly men in the workforce is projected to decrease during the year 2020 to 2040. Now, the whole thing doesn't decrease the whole time because we can see here that it's decreasing, and then it looks like it increases a little bit and then goes back to decreasing. So it looks like just between that time frame, it is actually decreasing. So this is the fun bit as you're kind of looking at these types of problems. We can really kind of look into all the different styles of questions that come out of one graph. Now, look at the same graph again, and what is the maximum number of elderly men in the workforce during that period? Now, when I say the word maximum, think about that. The word maximum normally makes a lot of people think about a high point, and that's exactly what you should think about. Think of maximum as a high point on the graph. Okay? So where's the highest point on this graph that I can see? Well, again, as I'm looking at it, my high point again, only looking at the blue. We don't care about the black. It's the blue that I'm really kind of concentrating on. It looks like 45.8 is that high point. So that right there tells me that my maximum is 45.8 million. And when did it take place? Now you'll notice that it says, what is the maximum number of elderly men during the period shown? Now I did say that it is 45.8, but I also want to add in the little caveat of when did that take place? Because that ordered pair, that point on a graph always has an XLA associated with it. So we do like to explain a little bit about where that came from, which in our case here was 1950. Okay, now we also look at things that may not have graphs, but as I look through the word problem, I'm not even reading it yet. The first thing I see that I draw my attention to is that I see this beautiful function. I notice the function notation right off the bat, and that's really important to kind of note there, okay? So let's actually go read through the problem and see what is it asking. But I have a feeling because there's a function notation in there, that's going to be part of our problem. So public health care expenditures for the period 1990 to 2012 can be modeled pretty accurately, approximated, so kind of a rounding model, by the function of E of t equals 738.1 parentheses 1.065 raised to the power of t. Now, E of t, that's that output, that y value, is in billions of dollars. Okay, so the y value or the output is in billions of dollars. And t is the number of years after 1990. Ooh, that's really important to catch there. Okay, now the question, so now let's see the question. What value of t represents 2010? What value of t? Well, I'm not really asking anything about an output in billions of dollars, am I? No, I'm not asking about healthcare expenditures. So really, I don't have anything about E of t here. Well, what I do have is t being the years after 1990. Now, this right here, it's highlighted, but I'm gonna underline it. I really need to bring that to your attention. This is gonna show up so much, and it's probably one of the biggest things the students make a mistake on when you are referring to these types of problems. Because a lot of students forget that we don't normally type in the years, we type in kind of like a reference number. So what value does t represent for 2010? Well, if t is the number of years after 1990, how many years have passed since 2010? Well, 20. Think about it. If you literally keep adding, you're going to get 2010, but what did you have to add to get to 2010? 20 years. So t itself is 20. And this is the most common practice that we use. Okay, so let's take that and take it to the next level. So really, a lot of the questions say, okay, so we get this beautiful function, and then it says approximate the public health care expenditure for 2010. Now, we just established that 2010 itself is t equals 20. That's what we just established, right? So I want to know, what is the public health care expenditure? Now, going back to think about what we learned a little bit ago, we kind of fancied this E of t, didn't we? And we said this was that beautiful function that we saw. But what I'm really seeing here is I'm seeing that I have to remind myself that E of t is the public healthcare expenditures in billions of dollars. So if 2010 happens to be t equals 20, and I want to know the public healthcare expenditures, again, that's E of t, that's what we talked about. What exactly do I need to do? Well, I have this beautiful function that tells me that E of t is equal to this, and there's a t there, and we just established t was 20. Well, ladies and gentlemen, I'm going to plug in 20. Now, I'm going to take a second here, and I want to make sure that you guys are understanding how to plug this into the calculator, because a lot of students make the mistake on this one. So pull up your calculator so you can kind of follow along a little bit here. So I'm going to plug this part right here into the calculator. So I'm going to start by 738.1 parentheses 1.065, close the parentheses, and then I'm going to hit this little symbol here. It looks like a little kind of hat. It's called the caret symbol. If you're looking at your keyboard, it should be the symbol right above the 6, okay? So I'm going to hit that, and what that's going to do is that's going to put it as a beautiful exponent there, and we're going to just type in what that was, which is 20, okay? Now, be aware, for those of y'all that might be trying to use the TI-83 in this course, the TI-83 is perfectly fine, but you're also going to want to have the same button set up as what I did, like the same steps, but it is going to show a little bit differently on your calculator, and I do want to show you what it looks like. So when you guys use that beautiful exponent, it's going to look like this, and it's going to have that caret symbol actually show up with the 20. So this will become a little bit more confusing later in the semester if you have a TI-83, but it's still going to give you the same answer. And we'll talk about the differences between the calculators with them and being very cautious there. Okay, and we can see that it was about $2,600.8 billion. Okay, now, well, still in the same area, So use the model to estimate the public health care for 2015. Now the question is can we be sure that this is accurate for 2015? Now, I bring this to your attention because we talked about at the very beginning of this model, and again, I'm going to kind of highlight some little thing. It says this was the public health care expenditures for the period of this to this. And this is what it can be modeled, accurate approximately. But it can only be modeled approximately accurate between these years. And when I look at the problem itself, it gave me the expenditures for 2015. Now, does 2015 fall between these years? Does 2015 fall in between here and here? No, it actually is a little bit larger. So can we be sure that it's an accurate estimate? Well, we can't. There's actually no way to predict it. Now, I am still going to type it in the calculator the same way by finding that this is going to be t equals 25, plug it into our beautiful equation that they gave us, and we get this answer here. But again, we also understand that we are not sure how accurate this prediction may be because we were only told that it's going to really work between here and here. This falls outside of that time range, so I cannot be 100% sure if that's going to work. Okay, that is 1.1. Hopefully, if you guys have questions, reach out to your instructor and ask. Or remind yourself that as you're doing the homework, make sure to write down the steps and maybe explain yourself how you are working your way through the problems to really kind of help you out.